Good afternoon. My name is Nakai George. My mentors are Drs. Bryce Orange and Marshall Parsons, with the additional guidance of Eric Baptiste. Welcome to my presentation, Design and Manufacture of Low-Cost Hardware to Benefit Precipitation Monitoring. The University of the Virgin Islands Eterman Observatory is home to several innovative technologies, such as the Virgin Islands Robotic Telescope, or VIRT. For this project, we aim to increase the technology readiness of a long-range radio communicator that detects precipitation. The purpose of this device is to monitor incoming rain and communicate any detection back to the observatory in order for the VIRT to close and be protected. Our project, built upon the first-generation design, improved the interface between components and external entities, and detailed the power budget to optimize solar power requirements. We hypothesize a good design for this device should be functional, durable, sustainable, expandable, and aesthetically pleasing. To reach our goal, we had many milestones to accomplish. We first had to review existing prototypes. This included electrical components, physical characteristics, size, and mounting. We also needed to research the exact function of each of these components, then analyze how they are connected to the external entities, such as the solar panel, antenna, and rain sensor. Next, we proposed a production design. We needed to take into consideration the ease of manufacture and installation, mechanical strength design, and environmental aspects. Then, we sought out to manufacture our new designs using 3D printed parts and store-bought items to save on cost, reliability, and availability. Lastly, assembling components for new packaging. This last milestone is currently being done due to pandemic setbacks. However, everything is ready to be built and serve their purpose. This is the second generation of our device. Each external entity on the box is able to function without interference from each other. The device is also compact enough to be placed on a pole or wall without using a substantial space. Each component is effectively placed within, which allows for extra space to expand the device's capabilities. The device is composed of store-bought items and 3D printed parts. For this device, we are 3D printing the mount of the wall, pole, rain sensor, and solar panel. We will be using a Form 2 SLA 3D printer. As you may or may not know, resin is a substance that hardens and becomes a polymer, basically 3D ink for the printer. We will be using a type of resin called Tough 2000, which is both durable and temperature resistant. This is one of the best materials to use for our device because it will need to survive the outdoors for long periods of time. This material will handle our tropical climate perfectly, protecting the device for years to come. The store-bought items needed to be both accessible and affordable because the device will be created multiple times. The prioritized bought components include a LoRa radio transceiver, weatherproof box, solar panel, antennas, and the RJ11 rain sensor. The estimated cost for all items is between $50 to $150. In the first generation, a 1.5 watt solar panel was used. It could barely store and supply this device power. I created various simulations to figure out the right solar panel we use. We then settled on using a solar panel that generates 10 watts of power. This is a surplus amount to self-sustain the device for days with the assumption of bad weather and power drain factors. We also decided to use a point-to-point wireless communication. PTMP is the ideal option because it allows for multiple scattered stations communicating to a base station. PTMP is in collaboration with a technique called polling. It's like a traffic light for communication transfer. Multiple stations wait for their turn to relay information to and from the base station. This device also is operating on a frequency of 950 MHz and has 8 miles of range. This is a heavily simplified version of the communication code for the RG11 sensor in the form of a flowchart, and the programming language is C++. After the program sets up, the loop will begin, starting with initializing tasks. Is sensor 1 able to respond, or is it working? No? Then this will be an error causing the loop to stop. But if yes, it is responding, then the program asks another question. Is it raining? Yes? Then display the detection of rain at the established sensor and continue to the next sensor. It's not raining? Well, there's no detection, but still continue to the next sensor. The program goes through the same process for sensor 2, and any number of sensors, then continues the loop until a sensor doesn't respond. This all basically means the program on rain detection should run forever until something happens to one of the RG11 sensors. There were many methods that went into the construction of the device. Modeling and sketching were used in conjunction for the design, structure, and functionality of the device. Simulating with graphs helped to visualize and predict how the device will operate in the real world. Programming was primarily used for communication with a rain sensor. Configuring the second generation of a lower rain sensor came with many challenges and setbacks. However, we were able to overcome them to prove our hypothesis. This low-cost, self-sustaining device will be able to function and stay intact, all while being able to expand. We can take the device further by increasing communication range and also turn the device into a drought or rain intensity monitor. There will always be improvements to make and functions to add. Nonetheless, this advanced warning rain detector will aid in protecting the vert at the observatory. Thank you to my mentors and funding source. For more information, please contact us. Thank you. Any questions?